Okay, the thing is, I forgot to record for today. I'll just quickly go over what we've done in the 1.5 hour. So first, as a review, um, it's a true or false question. So if the spanning set is not spanning set. So if a set of the given vector 1, 2, negative 1, 1, 2, negative 1 is a basis in R squared. So remember the definition of basis. Basically, we need to find a unique combination of alpha i's, and then we and if we can find a unique representation, then we say this is a basis. All right. Now, given these three vectors, so for any v equals v1, v2, we can write like we have to find a linear combination of these three vectors. Now let's see if we can find that. So set this v equals alpha 1 first vector, alpha 2 second vector, alpha 3 third vector. We go with alpha 1 would be, v1 would just be equal to alpha 1, 1, alpha 2 multiplied by negative 1, alpha 3 multiplied by 2, and sum of them. And similarly, V2 would be equal to alpha 1 times 2 plus alpha 2 times 1 plus alpha 3 times negative 1. All right, so given these two equations, we can further reduce these equations to, so if we just multiply by the second equation with the 2, with the extra 2, we can end up with this 5a alpha 1 plus alpha 2 equals v1 plus 2v2. So by multiplying the 2 on the bottom, we eliminated the alpha 3 on both equations. All right, but that's as far as we can go for the reduction or for reducing the equations. So if we have a v1, v2, and for a vector 2, 2, we know that 5 alpha 1 plus alpha 2 would equal to 6. That's by v1 is 2, v2 is 2, and we have like 2 plus 4 would be 6. So, and then we can end up with, for example, alpha 1 equals 1, then my alpha 2 would have to be 1 as well. And then my alpha 3 can be calculated from here. So one option of choice of, like one choice of alphas could be 1, 1, 1. But there are other choices. So if I have alpha 1 equals 4 over 3, then 5 alpha 1 will equal to 20 over 3. And 6 is basically 18 over 3. So we can calculate alpha 2 to be negative 2 over 3. And then similarly, substituting back to the second or the first equation, we got my alpha 3 to be 0. All right, I already found two combinations of alphas. Now there are more because I can take any alpha 1, then calculate alpha 2 and alpha 3. So we know that finding two of them means at least they're not unique, and not unique means it's not a basis. All right, then, however, these three vectors, although they're not bases, they're spanning. So they're a spanning set of R squared. And what does it mean? So one important concept in linear algebra is span. So given a set of vector, the span of the vectors is all vector v that can be written as a linear combination of the set of vectors. So I give an example. So given 1, 0 in R squared, the span of 1, 0 is basically anything with on the on the x-axis, if you think about the Cartesian plane. So any alpha in R, we can represent it as a linear combination of 1, 0. We just multiply by alpha. All right, now, so the span of a set we write as span set. So if the span of the set is the capital V, which means the vector space, then we say the set of vectors is a spanning set, or we call it a generating set or complete set. So for example, the standard basis, so given 1, 0, 0, 1, we say it is a spanning set of R squared because we can represent any vector. For example, 2, 2 is just 2 multiplied by the first vector plus 2 multiplied by the second vector. Or 3 next to 1 is 3 multiplied by 1, 0, next to 1 multiplied by 0, 1, and then we sum them. So we can represent any vector in R squared with these two vectors. So the span of these two vectors is R squared. However, it's not the only spanning set. So for example, if I just consider R squared, like R squared itself spans R squared because we can just do like 1 multiplied by the vector that we want and 0 on other vectors. All right, so my example on the top right here also spans R squared. Because for any V1 and V2, we can find some alpha 1, alpha 2, alpha 3 that gives us V1 and V2. So, so that means it spans R squared. All right. So then, why do we learn about the span? We say the basis has to be first span and second meet the uniqueness requirement. And the uniqueness is equivalent to something called linearly independent. So if I have a set of vectors and they're linearly independent of each other, then we will be able to find a unique combination of or unique coordinates so that we know that our vector is the basis. Okay, now what does it mean by linearly independent? So given vectors v1 through vn, we call them linearly independent if we can write alpha 1 v1 plus alpha 2 v2 plus all the way to alpha n vn equals 0 implies each alpha 1 or each alpha I equals 0. And this should be the only way that can get this equation to be 0. All right. AK, like this implication also known as there is no non-trivial linear combination of 0 vector. So non-trivial means, well, if I'm multiplying something to a vector, something to a vector, of course I have that alphas, like I have one solution to have all alphas to be 0. Then this is a trivial solution because any set of vectors will have this solution. I actually have one example right here. So if I have a standard basis of r squared, then I want to find a alpha 1 times 1, 0 plus alpha 2 times 0, 1 equals 0. The only option I got is to have alpha 1 equals 0 and alpha 2 equals 0. So this is the only option. But if I'm thinking about the example I did at the beginning of the class, so these three vectors, if we want to calculate a linear combination of them to be zeroth factor, then first, of course, all alphas can be 0. Like 0 plus 0 plus 0 is always 0. That's our trivial answer. But there are other options. For example, if I let alpha 1 to be 1, alpha 2 to be -5, alpha 3 to be -3, so like this, we would also get 1 multiplied by 1 plus -5 multiplied by -1 plus -3 multiplied by 2. That's on the top. And then on the bottom, we got 1 multiplied by 2, -5 multiplied by 1, -3 multiplied by -1. And these two, like this combination also gives us the zero vector. So this is one solution, and this is another solution, and there are more solutions. But having a non-trivial solution means that the set is linearly dependent. So it's not linearly independent means it's linearly dependent. All right. So that's the explanation for trivial and non-trivial. Now I have a proposition. So we say V1 through Vn are linearly dependent if and only if. So this is like implication in both ways. So V1 through Vn are linearly dependent if and only if there are some Vk can be written as a linear combination of others. All right, to prove if and only if, we usually prove both ways. So to prove, to prove the first direction, we assume the first statement is true, and then we prove that the second statement has to be true based on the first. So we suppose the first statement is true. Suppose V1 through Vn are linearly dependent. Right? Now, linearly dependent means there exist some coefficients, alpha 1, alpha 2, and through alpha n, that some alpha k does not equal to 0. Meaning that one of the alphas is not 0. All right, this is what we get from the linearly dependent. So given that, if we subtract, so we know that what one of them like within side, like if alpha k is not 0, so alpha k is right here. Let's subtract everything else on both sides. So subtract alpha 1, V1, alpha 2, V2, all the way through alpha n, Vn, just accept this alpha k, Vk, and on the right side as well. So on the left side, we are left with alpha k, Vk, and on the right side is everything else but negative. Okay, and then this alpha k is just a scalar. I can divide alpha k on both sides. So dividing this whole thing by alpha k is the same as divide each term by alpha k. That's like the multiplicative distributivity. All right, now this negative alpha I over alpha k is just a scalar. So if we expand the sum, it's just the scalar of v1, scalar of v2 plus something plus the scalar of vn. But we need to skip when I equals k. So from I equals 1 to n, but I cannot be k on the right side. All right. Now, if I can write vk as a linear combination of other vectors, that's actually just our second statement. So now we've proved that the first direction, proving it backward to be finished. All right, now for the, did I say backward? The forward direction is finished. Now for the backward direction. So now now backward direction is to assume the second statement is correct. So we assume some vk is a linear combination of others. So some vk is a linear combination of others, means that we can write vk as a linear combination of other vector. So this is just a translation from the English sentence to the mathematical sentence. Right. And this equation means we write vk as beta 1, v1, beta 2, v2, all the way to beta n, vn. But without the k. Without the vk. All right, now, so since we want to prove that they are linearly dependent, and we know that for linear independence, we want to set the equation to equal to 0, and we see if we can find a non-trivial solution. So let's subtract the sum on both sides. We subtract the sum, we subtract the sum. On the left, we're left with vk plus the sum, but with a negative coefficient. And on the right side, we're just left with 0. All right, on the left, we have vk. So vk, if you think about it, it equals 1 times vk, because 1 is the scalar multiplicative identity. So we rewrite this vk to 1 multiplied vk. And then we have other vectors with coefficient negative bi. Right. Right now, I do not know what are the bi's, but we know that for vk, the coefficient is 1, it's not 0. So this linear combination is non-trivial. because AK is 1. Because like having alpha 1, alpha 2 to be 0, 0 is not the only solution. It's not like there exists a solution with AK equals 1. All right, that means V1 through Vn is linearly dependent. All right. Now we have a proposition. V1 and Vn are a basis of V means that, like, if and only if, first, they span the vector space. Second, they are linearly independent. So this is usually used as a definition of basis. We can do the proof forward and backward. So if they're a basis, then they have to span, they are linearly independent. And if they span and linearly independent, we know they're a basis. I skipped the proof, but it should be able to be, like, this should be able to be found online. All right, now I have another proposition. Every spanning set V1 through Vn contains a basis of V. So at the beginning of the class, this example, we saw that there are sets that spans, but it's not a basis. And this proposition says that if a set spans, then we should be able to find the basis inside of it. So in this case, let's consider the first two elements. All right, these first two elements, we claim that this set 1, 2, next one, 1 is a basis of R square. Now we prove that. First, we prove that they span B or span R square. So do they span R square? We can write for any vector V, V1, V2, span means we are able to find alpha 1 and alpha 2 that if we do the linear combination, we get any vector V. Right now, we write V1 equals V1 equals alpha 1, 1, alpha 2, 1, and V2 equals 2 alpha 1 and 1 alpha 2. Right now, I have two equations. So if we just add them together, I got V1, V2 equals 3 alpha 1. So alpha 1 equals V1, V2 over 3. And alpha 2, we substituted back to the first equation. We got V1 plus V2 over 3 minus V1. All right. And then we further simplify it. It equals V2 must subtract 2V1 over 3. All right. Now, since we can represent any V with alpha 1 to be this, alpha 2 to be this, so it means that this spans R squared. So it spans. All right. Now let's check. Suspense. Now let's check the second requirement. Let's verify they are linearly independent. So linearly independent means I should be able to find a combination equals the zero vector, but this combination should be unique, should be this trivial solution. So similarly, we set the linear combination equals the zero vector. And we found that alpha 1 plus alpha, subtract alpha 2 is 0. 2 alpha 1 plus alpha 2 is 0. And then we already know this alpha 1 is v1 plus v2 over 3. So v1, v2 are both 0 in this case. So it'll be alpha 1 will be 0 plus 0 over 3. It will be 0. Alpha 2 is 0 minus 2 multiplied 0 over 3 is 0. All right, so this is our only solution. Alpha 1 and alpha 2 equals 0 and 0. If we only have this trivial solution, then we say these two vectors are linearly independent. Now we know the spans. Now we know they're linearly independent. We conclude that this whole thing conclude that this set 1, 2, negative 1, 1 is a basis of R squared. All right. Then brief introduction to linear transformation. So this time, if I have two vector spaces, V and W, we call a function, or in this case, we call a transformation, linear if this transformation mapping from V to W satisfies first, the transformation of the sum of two vectors is the sum of the transformation of either vector. Second, the transformation of a scalar multiplication of a vector is the same as the scalar multiplication of the transformed vector. And then, for example, if I have a transformation mapping from R squared to R squared, I'll just define it. T equals a T of V1, V2 equals 2V1 plus V2 over and V1. Now the question is this linear? To check if this is linear, we have V and U belongs to R squared. And let's define V to be V1, V2, U to be U1, U2, and define alpha to be a scalar. Now, let's check the first equation if it's true. The left-hand side is the transformation of the sum of vectors. So the sum of vectors is just we sum it component-wise. So the transformation of this vector that equals 2 multiplied by the first component plus the second component, and on the bottom is the first component. Okay, the right-hand side is first we find T of V, and then we find T of U, and then sum them together. So T of V is right here, T of U is right here, and then we sum them. So first component plus the second component, and bottom is just both the sum of two second components. All right, and then we can take a 2, factor 2 out, and rearrange this first component. And now we found that these two are the same. So we say left-hand side equals the right-hand side, the first equation, we know this is true. Okay, now let's look at the second equation. So we want to prove that the transformation of a scalar product equals the scalar product of the transformation. So similarly, left-hand side, you multiply by the scalar first, and then you do the transformation. So scalar, and then transformation is 2 multiply the first component plus the second, and bottom the first. And similarly, we do on the right-hand side, we do this transformation first, and then we do the scalar product. So after the transformation, we got this and multiply by alpha. So on the top, I just distributed this alpha, and then on the bottom, I have alpha u1. So now, these two equals. So now we can again conclude left-hand side equals the right-hand side. And therefore, since it satisfies both equations, we say T is a linear transformation. All right, that's the quick version for today. 40 minutes.